of Serada Julius. I'm going to take you through continuity of limits of functions, as you see, on 16th of September 2025. We are to discuss continuity of limits of a function. First of all, a function is said to be continuous at a certain point under certain conditions. The conditions are three. One, a function is continuous at a certain point when three conditions are satisfied. One, first of all, a function to be continuous at a certain point, it should be defined. How? The function to be continuous at a certain point, it should be defined at that point. For example, let's have a function as f of x is equal to x cubed plus 2x plus 1 out of x minus 1. For this function, f of x is equal to x cubed plus 2x plus 1 over x minus 1. For this function to be continuous at a certain point, it should be defined at that point. Let's say, for example, if the value of this function at x is equal to 1, if we try to substitute to get the function value, f of 1 will be equal to x cubed, x into 1 cubed plus 2 into 1 plus 1 out of 1 minus 1. Getting this is a 1 plus 2, 3, which is 4 over 0. So this one is mathematically wrong, meaning that this value is not continuous at 1 because we are getting a value which is undefined at this point. So for a function to be defined at a certain point, it should be defined at that point, meaning that we should be able to get at, let's say we have at x equals a, we should be able to get a value at that point. F of a must exist. Then from there, the second condition is for a function to be defined at a certain point, the limit of a function must exist. Where? For, let's say when you have this function, for this function to be continuous at a certain point, it should have a limit at that point. Let's say the function must have a limit at that particular point. Or the limit of a function at that point must exist. If at all we find a certain function which does not have a limit at a certain point, that clarifies that that function is not continuous at that point due to this condition. So for any function to be continuous at a certain point, this condition must be satisfied. Then the third condition is for a function to be continuous at a certain point, the function value must be equaling to the limit of a function at that point. Let's say we have a function f of x, a function to be continuous at a certain point. The function value must be equaling to the limit of a function at that point. That is to say, for a function to be continuous at a point, the function value f of a, let's say at a point a, must be equal to the limit of a function as x approaches a. So, if at all we get to find ourselves that we have a functional value and the limit of a function at the same point, that function is continuous at that point if and only if the function value at that point is equal to the limit of a function at that point, which is stated mathematically as written here. So these are the three conditions that must be satisfied for a function to be continuous at any point. First of all, the function to be continuous at a certain point, it should be defined at that point. Meaning that if we substitute to get the function value must be defined. Then the second, the function must have a limit at that particular point. So the limit of a function must exist at that point. The third, the function to be continuous at a point, the function value at a given point must be equal to the limit of a function at that very point. These are the three conditions that should be satisfied for a function to be continuous at a given point. And from there, we are going to look at some of the examples of how to define the continuity of limits of functions at given points. Before that, we have continuity of limits within an interval. We have what we call continuity of limits. Subchapter under continuity. Continuity of limits. Continuity of limits of functions within an interval. Continuity of limits of functions within an interval. What does this one mean? So at some circumstances, we might find ourselves when we are given a point, we are given a function f of x that is continuous in an interval a, b. At certain circumstances, we may be given that a certain function f of x is continuous in an interval, this one a, b. So for a function to be continuous in a given interval, that function must be continuous within all those points within that interval. Let's say when we are given a function that it is continuous, if f of x is continuous in an interval of let's say 2, 6. What does this one mean? This means that a certain function f of x is continuous at a point 2, 3, 4, 5, and 6. This is the meaning of an interval, meaning that all the points enclosed within this interval, that a certain function given is continuous at all of these points. So we must also get to know about continuity of functions within an interval. Then from there are some issues we must note. Because we have different types of functions which we may be given. We may be given a polynomial function. For this polynomial function, what we must get to know, for the polynomial function, they are continuous everywhere. Polynomial functions are continuous everywhere. If we talk of the polynomial function, those are the linear functions which we are given highly. Like if we are given p of x as equal to x cubed plus 4x minus 1. This is an example of a polynomial function. So for such a type of functions, for these functions, they are continuous everywhere. Then another type of function we have are the trigonometric functions. For the trigonometric functions, for them, they are also continuous everywhere, but in their domain. They are continuous within their domain, which may be given. Like for a function like p of x is equal to sine squared x plus 1 over cos x. This is an example of a trigonometric function containing some bit of trigonometry, sine squared x cos x. For such a type of functions, they are continuous everywhere in their domain. Then another type of functions we may have is what we call the rational functions. The rational functions. This type of functions where we have a numerator and a denominator. For this type of functions, they are continuous except when we happen to get the value of the denominator is 0. Like let's say we may have x cubed plus 2x plus 1 out of x minus 1. This is an example of a rational function. This function is continuous everywhere except when the denominator happens to be 0 when we substitute in a certain value. Let's say if we want to look at the continuity of this function at x equals to 1. If we try to substitute to get the function value f of 1, let's say this is f of x. F of 1 will be a 1 cubed plus 2 into 1 plus 1 out of 1 minus 1. Getting this will be a 1 plus 2 plus 1 out of 0. Getting a 4 out of 0. Meaning this function is not continuous at a point where x equals 1. Why? Because the denominator is 0. Because you can't divide 4 by 0, meaning that the functional value at x equals to 1 is undefined, meaning that this function is not continuous at x equals 1. So these are also some of the important issues you must note. We've said polynomial functions are continuous everywhere. Then the trigonometric functions are continuous everywhere in their domain. Then for the rational functions, they are continuous except when the denominator is 0. So from there we are going to look at some examples on calculations on how to find out the continuity of limits of functions at certain points when we are given some points define the continuity of functions at a given point. We can get some good examples from here. Check whether the function x squared minus 4 out of x minus 2 is continuous at x equals 2. How are we going to deal with such a question? They have told us to check whether the function x squared minus 4 out of x minus 2 is continuous at x equals 2. Then if we try to look at our function, we can say let f of x equals x squared minus 4 out of x minus 2. If we try to factorize out, we can look at this one, x squared minus 4. We can factorize this one out and we come up with x plus 2 out of x minus 2 over x minus 2. With further simplifying, we can get x plus 2. Then from there, if we are to define a limit of this function as it approaches 2 at x equals 2, limit of f of x as x approaches 2 will be equal to a 2 plus a 2, which is equal to a 4, meaning that this is our limit of a function at x equals 2. Then from there we are going to look at the function value as x approaches 2. When we are looking for a function value, we just substitute in that value we are given, because here we are given x equals 2. We have to substitute in here to get the function value. If the function value happens to be the same with the limit of the function at x equals 2, meaning that this function could be continuous at x equals 2. Okay, let's look at what we call the function value. The function value we just substitute in directly. Then function value f of 2 will be equaling to 2 squared minus 4 out of 2 minus 2, which is a 0 over 0, getting a 0. Then from there, if we try to look at our computations, we'll get the limit of a function at x equals 2 as 4. Then the function value is 0. Then if we try to recall for the conditions, for a function to be continuous at a certain point, the function value must be equal to the limit of a function at that point. So how are we going to conclude here? Since f of 2 that is not equal to the limit of a function as x approaches 2, so the function is not continuous at x equals 2. So this is our conclusion. From here, what we have got, since the function value f of 2 is not equal to the limit of the function as x approaches 2, so the function is not continuous at x equals 2. Then that has been our first example. If we try to look at another example about the continuity of limits of functions, if we try to look at another example about continuity of limits of functions, provided we are given our example 2 as f of x is equal to x cubed, then a minus x. From here we are given when x is less or equal to 2, then x greater than 2. Then this is our function. The question says, find the scalar for which f of x is continuous at x is equal to 2. That's our question. Find the scalar. This is alpha. For which f of x is continuous at x equals 2. We are given a certain function f of x is equal to x cubed when x is less or equal to 2, a minus x when x is greater than 2. Find this. We are told to find the scalar for which f of x is continuous at x equals 2. How are we going to deal with such a function? So, because so far we've been dealing with a rational function as well as a polynomial function. Then here we are given such a function. How are we going to deal with it? First of all, with such functions, we are going to deal with the left-hand limit and we are going to deal with the left-hand limit and the right-hand limit. For a function to be continuous at a certain point, such a function, the left-hand limit must be equal to the right-hand limit of that function at a certain point. Then, for example, if we are dealing with such functions, the limit of a function, the left-hand limit, of a function at a certain value must be equal to the right-hand limit of a function as x approaches the same value, as well as equal to the function value of that point. This condition must be satisfied for such a function to be continuous at a certain point. Let's say at a point, for this case I have used x equals a. At a point at x is equal to a, meaning that the left-hand limit, which is denoted as limit of a function as x approaches a, must be equal to the right-hand limit as x approaches a, as well must be equal to the function value. As we said so far, that for a function to be continuous at a certain point, the limit of a function must be equal to the function value. But for this case, if we try to see, we are going to have the left-hand limit and the right-hand limit. Again, no matter the limit, the left hand and the right hand must be equal to the function value, meaning that the left-hand limit must be equal to the function value, as well as the right-hand limit must be equal to the function value. If we try to see, here we are given our x as 2. What are we going to say? For a function to be continuous, for f of x to be continuous at x equals 2, what should we follow? The limit of a function as x approaches 2, the left-hand limit, which is denoted like this, must be equal to the limit, the right-hand limit as x approaches 2. So, as well as equal to f of 2. That's how we are going to deal with such a function. Then from there, how are we going to look for the left-hand limit and the right-hand limit? From there, we look for the left-hand limit. If you try to see, we are given x cubed when x is less or equal to 2. Then we are given alpha minus x when x is greater than 2. These are functions. F of x equals x cubed when x is less or equal to 2. Then f of x equals alpha minus x when x is greater than 2. So, what do we consider here? This less than sign, the first function, is going to act as to be part of our left hand limit, and then the greater side, we put it on the right hand limit. Then we substitute. Then here we have limit of a function as x approaches the left hand limit. We substitute x cubed is equal to the limit as x up the right hand limit as x approaches 2, which is alpha minus x. Then from there we substitute. What are we going to say? This is, we substitute because we are given find the scalar for which f of x is continuous at x equals 2, meaning that we are going to substitute x as equal to 2. Then we say 2 cubed is equaling to alpha minus 2. From here we are going to solve mathematically. Then 2 cubed we are going to get 8 as equal to alpha minus 2. Then if you try to correct like terms, this one goes this side, getting 10 as equal to alpha. This implies that alpha equals 10. So by getting the value of alpha, we are done, because we are told to find the scalar for which f of x is continuous at x equals 2. Then after there we restate the function, meaning that this function is f of x equals x cubed for x less or equal to 2. Because we got our value of alpha, which is 10, meaning that we are going to get 10 minus x for x greater than 2. So there we are done. So our function must be like this, for which this function is continuous at x equals 2. So that's how I can take you through the continuity of limits of functions.